Welcome everyone. It's our great pleasure to have Navinda Kottege here from CSIRO Data61. So Navinda is the group leader for robotics at Data61, and he was also the principal investigator and project lead for the CSIRO Data61 entry in the DARPA Subterranean challenge, of which they had some really exceptional results, and I think that's mostly what he's going to talk to us about today. So Navinda has been at CSIRO since 2009 after completing his PhD at the Australian National University. Since then, he's been kind of rapidly rising through the ranks at CSIRO to now be leading the robotics efforts there. He's also a senior member of the IEEE and past chair of the IEEE Queensland chapter for control systems and robotics and automation for the IEEE. And he's an adjunct associate professor at both Queensland University of Technology and the University of Queensland. So without further ado, over to you, Navinda, and thanks for coming to speak to us today.
Thank you, Ian. Today I'll talk a little bit about what happened to our team at the DARPA Subterranean Challenge. I will be a little bit light on the technicalities. Do hit me up at the end with questions. I'm happy to kind of go a bit deeper. I'll try to do a little bit of storytelling where you have tragedy and triumph against unfavorable odds and all of that. So hopefully you'll enjoy it. So before we start, I'll do a super quick overview of CSIRO for those who are not familiar. So CSIRO is a national science agency. We are 5,500 people across 57 sites in Australia. We do research in very broad topics from agriculture, food and agriculture, health and biosecurity, space and astronomy, energy, mining and minerals. And there's a business unit called Data61, that's where I come from. And Data61 does research in many data science related areas, robotics, cybersecurity, computer vision, so on and so forth. So our lab is in Brisbane, and my group currently is just over 100. We have about 60 full-time staff members, and we have about 40 odd students and affiliates. Apart from 3 of them, everybody's in Brisbane. So it's a very Brisbane-centric group that I have currently. And this slide is meant to represent some of the robots that we've either built or worked with over the last 2.5 decades. And again, coming from ACFR, I'm sure you guys are not strangers to things that don't typically look like robots. And then we have drag blinds, automated drag blinds. We have automated rock breakers there, load haul dump trucks, 30-ton forklift trucks carrying 8-ton vats of molten aluminium, and then things like that. And then we also have some robots that you'll be familiar with, like the Boston Dynamics robot there. In terms of the areas of research that we're currently focusing on, that's what I have on the right-hand side. Situational awareness, which includes our SLAM technology, complex area navigation. Those 2 are things that we have fairly mature capability in. And then the bottom 2, human-robot teaming and robot-world interaction, are areas that we are currently ramping up. And a robot-world interaction includes things like mobile manipulation, but in a field robotics setting. And then we are also ramping up on 2 newer areas, embodied AI and soft robotics, where we are building soft robotics grippers and things like that. All right, so topic of today. I'll start with explaining a little bit about what the DARPA Subterranean Challenge is for those who are not familiar, and about what we did and what we achieved, and a little bit about how we achieved all of that and why it all matters. So the DARPA Subterranean Challenge, starting with DARPA, I'm pretty sure most of you are familiar with, but I'll kind of give the spiel that I usually do. So DARPA is the premier defense research agency in the US, been around for quite a while, and known for quite some significant things. Back in the 60s, they invented the internet. So I'm sure most of you have heard of ARPANET, that is before DARPA picked up the D in the acronym. And then more recently, in the last 2 decades, they started setting up some pretty significant robotics challenges, grand challenges in robotics. and the aptly named DARPA Grand Challenge back in the early 2000s was to send an uncrewed vehicle across the Mojave Desert. The team that won from Stanford got hired by Google, and that's what morphed into Waymo currently. So the whole autonomous vehicles industry was kickstarted through a DARPA challenge a while back. Fast forwarding to 2017, the latest iteration of these challenges called the DARPA Subterranean Challenge, or SUBT for short, was announced. And then we put in a proposal and we were successful to receive funding to compete. So what happened was, out of all the applicants, they selected 7 teams to be funded to compete. So we were one of the 7 teams. There were 5 other self-funded teams with a total pool of 12 teams. And what's significant is, out of the 7 teams that got selected for funding, we were the only non-US based prime organization. All the other 6 teams had their primes based in the US. So that was a significant win for Australia as well, to be recognized for our field robotics capability. And then the challenge was to send a team of autonomous robots into completely unknown underground environments. And then the task was from there to perform what's essentially a scavenger hunt to look for a series of predefined artifacts, things like thermal mannequins representing human survivors, fire extinguishers, mobile phones, climbing rope, hard hats, backpacks, hand drills, pockets of high concentrations of carbon dioxide, air vents. I'm probably missing a few, but these are all things that a human team of search and rescuers would look for in the aftermath of a natural disaster or industrial incident when they're looking for human survivors. So that was the basis of this challenge. The robots had no guarantee that they would be able to communicate back to the base station. These environments were severely constrained when it comes to radio communication. Only one human supervisor is allowed to connect to a computer that can talk to the robots. So that was a constraint there. There wasn't a limitation on the number of robots that you can deploy. So it was up to the teams to deploy as many robots as they want. The time was 1 hour. And then within that 1 hour, we needed to go and find as many artifacts as possible. So there was no requirement to retrieve anything. There was no requirement to bring the robots back. So all you wanted was the data of the correct object class and the location. So you can kind of boil it down to that, like you need correct location of the object and the correct class. It sounds easy enough, but what it hides is all the complexity of that being a localization challenge, a mapping challenge, a perception challenge, a navigation challenge, an autonomy challenge, mobility challenge, navigation challenge, all of that. And that also was the beauty of the whole thing, because you could explain what the challenge was to a non-roboticist quite easily, under a minute, and you'll get it. You'd know what to do. But then the robotics would start sweating. So I'll play a quick video to give you an idea of what the scoring or what scoring a point was like challenge.
Here's how to win an event in the DARPA Subterranean Challenge. Find the most artifacts in the shortest amount of time. When or if a team system locates an artifact, it has to report not only the type of artifact, but also its spatially referenced location to an accuracy within 5 meters. A valid report earns 1 point, but teams are granted only a limited number of reports, so they can't just guess until they get lucky. Sound easy enough? Think again. Teams have to send their systems through dynamic terrain, over, under, and around obstacles, in austere navigation conditions, pushing the limits of their endurance, and in conditions degrading sensing capabilities and severely constraining communications. Teams will be permitted multiple time runs through the course, but between each run, the course can be changed. Obstacles added, passages blocked or unblocked, and artifact locations can be changed. So teams need to be agile, adaptive, and accurate if they want to emerge victorious in the sub-T challenge.
So that gives you an idea of what was required. And in terms of the environment, they divided it into 3 subdomains. First was the man-made tunnels, like mining tunnels. Second one was underground urban environments. So any built environment could be a subway system, sewer system, or any other industrial infrastructure underground. And then the third one was natural caves. So over the 3 years, starting from late 2018, they had 3 circuit events planned. So first one was the tunnel circuit event, which was held in a coal mine in Pittsburgh. And then the urban circuit was held in Satsop, Washington. That was a fun event in an uncommissioned nuclear power plant, which had 2-meter thick lead impregnated concrete walls. So nothing radio frequency gets through those. And then the third circuit event was meant to be the cave circuit event scheduled for August 2020. As we all know, that's not going to work because of COVID. So that particular event was cancelled, and all the teams participating were encouraged to have their own cave event in their local area. So we took up the challenge and we held our own DARPA style cave circuit event in the Chillago cave systems in far north Queensland. So after competing in these 3 circuit events, all the data and all the performance metrics were evaluated by DARPA, and then in the end they selected 8 teams to participate in the grand final that was held in September 2021 last year. So we were selected as one of the finalists. And what they did was they did a fantastic job in setting up a fully artificially made course that included challenge elements from all the 3 subdomains. So tunnels, underground urban, and cave. So they held this in Louisville, in the Louisville Mega Cavern. It was a massive limestone quarry that was dug into the side of a mountain. And within that, they built this course. So the next video will explain a little bit about that.
We're in the Louisville Mega Caverns because it gives us wide open canvas to be able to paint our vision of what the Sub-T Challenge final event is supposed to look like, which is a mashup of 3 different subdomains: tunnel, urban, and cave. Each of the circuit events was focused on a particular subdomain, and that allowed teams to really zero in on what technologies work for that subdomain. The final event is about putting all of that together, bringing it into an integrated capability in that epic grand finale course.
And what I should also mention is they had 2 tracks, the systems track and the virtual track. So we participated in the systems track where physical robots were deployed. The virtual track was all based on simulation. So there were some teams who participated in the systems track, also participated in the virtual track, which we didn't. What was interesting though in the virtual track, the way they did was they had a series of different virtual environments, and the teams had to deploy robots and they would have to perform well in each of the different scenarios. And in the final of the virtual track, there was some Australian representation, not by us, but long time ago using our technology, we scanned the Genolan cave system in New South Wales, and we made that dataset public. So DARPA actually used that dataset to create a natural cave environment for the DARPA Sub-T virtual track. So all the teams from around the world, they actually send their robots virtually into the Genolan cave. So just pretty cool. And to our team. So this is just a subset of our team. We partnered up with 2 other institutions, 2 other organizations. So Emerson, that's a drone autonomy company that our lab spun out about 3.5 years ago, based in Brisbane. So they provided drone autonomy, and we also partnered with Ron Arkin, Georgia Tech in Atlanta, Georgia. As you can see from the list, majority of the capability did come from CSIRO. Emerson provided drone autonomy, and then Georgia Tech worked with us to develop a multi-agent coordination system. And in terms of the platforms, I have a later slide that shows the full set of platforms that we used over the 3 years. But these 3 are the platforms that we were planning to deploy in the final event. In the end, the smaller track robot wasn't deployed. We had two of the larger track robots built by a Brisbane-based company called VIA5, and each of those carried a drone on the back, an Emerson drone, and then we had two of the Boston Dynamics Spot robots. So in total, we deployed 6 agents in the final, 2 track, 2-legged, and 2 drones. This slide shows a little bit more the hardware setup that was used. And each of the ground robots had the same autonomy and sensing payload. So what we call the cat pack, that has a spinning velodyne with some RGB cameras, 4 RGB cameras at the base. And that's where our SLAM system is running. So SLAM is processed in real time, and including the object detection, visual object detection as well. And then we have carbon dioxide detection, Wi-Fi and Bluetooth detection, and all of that incorporated into the system as well. And the other thing that we had was we had droppable communication nodes. That's what you see at the bottom right. So these nodes could be carried on the back of the larger track robot. So each large track robot could carry 4 of them to try and maintain a communication backbone as you enter the course. So this video shows deployment of a comms node. Not very elegant, but if you wait, you see what happens. After time delay, the ground plane opens up and the antennas pop out. And then you would have seen the drone being deployed from the back of the track robot as well. So we competed over the 3 years. We got into the finals. We were all raring to go. But then due to COVID, CSIRO decided that it wasn't safe to send CSIRO staff over to the US in September last year, which was quite devastating for us, but that's what we had to deal with. So within a very short period of time, we had to come up with a backup plan. So we shipped our robots, and we had to train our subcontractors to use our robots. Mainly the Emerson crew was based in Brisbane. They weren't dealing with any of the UGVs at that time. They were only dealing with the drone part of the whole team of robots. And then we got staff from the CSIRO US-based office. That we have an office in California. And it's not a research lab, it's mainly marketing and partnership staff, but they were really enthusiastic. They want to come and help the team, which was great. And then we were also fortunate to have a couple of our lab alumni who currently work in the US, who took leave from their day job and decided to come and help us, which was good as well. And then for us, what happened was we rented a bunch of these double telepresence robots, and we were logged in from Brisbane. For 2 weeks, we were working US East Coast hours from Brisbane, which was fun. So bottom right, you see some of my team. That was around 2 a.m. Working throughout the night to provide remote support to the team that was up in Louisville. We rented a large warehouse, logistics warehouse, where we did pretty rigorous testing for about 1 week. And this is a view that I got when I was logged into one of the telepresence robots. And we had to do some emergency repairs, hardware repairs on our robots, because none of the team that went there, we didn't have anybody from our engineering team. So we had to do some emergency electronics repairs on the spot. And we also had to replace a gear of one of the large track robots. So what we did was we had 3 of each. We kept 1 of each back in Brisbane. So this was a case where we were disassembling our robot back in Brisbane while they were doing it over there. So it was a little bit like a movie. It's not the blue wire, cut the red wire type of thing. We all very exciting because we didn't have a lot of time, because the way they ran the final event was they had 2 preliminary runs back to back on 2 days, and then they had the final run. So if we damage a robot in one of the preliminary runs, you just need to have that robot ready the next day to run again. So not a lot of margin for error. Yeah, and there was a point where we were really considering not even deploying robots in the preliminary run. So the funny story is in the early circuit events that we had, so we were very slowly moving up the leaderboard. So the first event, the tunnel circuit event that happened in Pittsburgh, we were 5th in the leaderboard. And then in the urban circuit event, we moved up to 4th in the leaderboard. But since the cave event didn't happen, we kind of extrapolated and said, we probably would have been 3rd in the leaderboard. And we naturally assumed that in the finals, we should be able to be in the top 3. So that's what you do. So you extrapolate with just 2 data points. But then when the whole COVID thing happened, we had to really lower our bar down. Like it was being in the top 3, going down to don't embarrass ourselves. So that's the reason why we were considering not deploying robots in the preliminary runs, because they weren't scored runs. That was to just give us familiarity of the environment. But if we broke any robots, we won't have any robots to deploy in the scored final run. So what we did was we deferred the decision to the team that was over there. We said, but it's up to you guys. Tell us whether you're confident enough. So what we did was we deployed about half of our fleet. So out of the 6 robots, we deployed 3 robots in the preliminary runs. What completely surprised us was after the 2 preliminary runs, we were top of the leaderboard in the preliminary scoring. So what they did was they used the scoring to decide the run order for the finals. So that score didn't carry over. And suddenly we were the team to beat. So the other teams were kind of telling us, you guys are the team to beat. And that was a very strange feeling because, as I said, we kind of went down all the way to, don't embarrass ourselves. So we were, because we were the top of the leaderboard in the preliminary runs, we went last. And what I'll do is I'll play a video of what happened in that final 60 minutes of the run. And this is to orient you to that video. On the left one screen that you'll see is the communication connectivity that's based on RSSI. That's where the base station was. That's the entrance to the circuit. That's where the robots are deployed from. The links, green is good. That's good connectivity, as it tends to as red, poor connectivity, and sometimes you'll see the links disappearing as well. By the time it goes to red, you're hardly getting anything through. And then you'll see the score and the remaining time and the remaining number of reports. And that's another screen. This is one of the views that the human supervisor at the base station would see. Now, that is not a post-processed view. So this is a post-processed view. So you'll see the full underlying map in this view, whereas on this view, you would only see the information that the robots had sent through to the base station. You'll see these colorful spheres popping up. So those are the different artifacts that we are scoring. And if it's appearing as colored, that means we've scored a point on that. And then you'll see some messages popping up. And what I forgot to mention was we gave names to the robots. So the 2-legged robots, I hope most of you get the reference. They were named Bluey and Bingo. And then the 2 tracked robots were Rat and Bear. Yeah, so let's play the video and see what happened. So early in the phase, you'll see one of the legged robots, Bingo, making good progress into the course. But then it loses communication. And it's on its own doing a beyond comms exploration mission. As far as the human supervisor is concerned, he has no clue what the robot is doing. As far as he's concerned, the robot is lost. But it's doing a pretty good job in exploring the large cavern. So this is the cave part of the circuit. Middle part is the urban, and the other one was the tunnel circuit. So this is a view from the base station. Bluey. I do apologize for Bluey being yellow, which kind of does my as well. But you'll see Bingo green in this view.
So what about the physical scale, for example, how far across?
Each cell is 10 meters. So at this point, that's all the information the base station had received. So comms lost. So as far as the human supervisor is concerned, doesn't even know that that part of the course exists. And this is what Bingo was actually doing. So this is from a DARPA camera that we received later on. It comes to an unfortunate end there. It's beyond comms, but it has a lot of valuable information that it had collected. It has a bunch of detection. So that's where it is. And now that is Bluey, again, beyond comms, doing a fantastic job in exploring a subway station there. And you'll notice something interesting happens with Bluey. Very briefly, it connects to Bingo, and then it connects back to the base station. And suddenly we get all these circles back, and we now know that part of the course exists. And then in the meantime, one of our big track robots, pardon the pun, got detracked on a rail track. So it's immobilized, it's blocking the path as well. It's got a drone on the back, and the drone is useless at that point as well. Now, Bluey had met Bingo, collecting all the data, makes a valiant attempt to get back to comms. But unfortunately, that too slips and falls beyond comms. At this point, we only have one mobile robot, which is Bear, which has a drone on the back. At this point, the human supervisor knows where the disabled robots are, so he's desperate to send a robot to mule the data back. But this robot has a drone on the back, which makes it too large to fit through the narrow passages of the caves. So that's why he has to send Bear over. So he tries to go through there, can't go through because Rat is blocking the way. Needs to come here, over here, because that's another large cavern, deploy the drone to get the form factor small enough to fit through the narrow passage of the cave circuit. And look at the time. So we got less than 3 minutes at that point. Connects back and connects the data back to the base station. And we score the last point with 25 seconds to spare. So you see the comms connectivity again. And this is the last minute at the base station. So we got a pit crew of 10 who helps to set up the robots, but after the setup time, when the timer starts, only one human supervisor, that's Brendan there. He's connected to the robot. So look at the time. Notice around 25 seconds, when there's 25 seconds remaining, you'll see the score going up. And the other bit about the number of attempts, there were a total of 40 artifacts, but they only allow you 45 attempts as well, so you can't keep guessing. So we scored 23 points with 13 reports to spare. What they didn't know at this time was we just tied for the top score. Because the teams are sequestered, these teams didn't, the team didn't know what the top score was at that time. We knew because we were logged in from Brisbane. And what was very frustrating for us is that we had 4 more accurate artifacts that were still streaming, which obviously we couldn't score. We had enough attempts left. So if we had another minute, not even a minute, maybe another 30 seconds, we would have scored 2 points. So I'll show you another video. This is from the GoPro footage on the 2-legged robots, just to give you an idea of what was going on and to give you a sense of what the course looks like. So this is Bingo exploring beyond comms. And this is one of the special artifacts that I didn't mention, that was called the DARPA cube. It was a glowing perspex cube to mess up any visual color-based object detection because it would change color constantly. So this is an autonomy behavior that we program into the robot. So if our traversability estimation sees a gradient below a certain number of degrees, it'll turn the robot around and walk backwards. That's due to the morphology of the legs of the Boston Dynamics robots, because it's more stable going down a slope backwards, including stairs. And this is a longer sequence of what you saw earlier. It actually digs up a power cable that DARPA had buried. I don't think DARPA intended for anyone to do that. It almost tripped, but didn't. And if you notice, that's actually water. That's real water dripping down. And these robots are not IP rated, by the way. So we were pretty lucky that we didn't get water in any of the wrong places at that time. And as you can see, this is pretty challenging terrain, even for a human to walk on. And those robots are remarkably capable in terms of what they are and what they can do. And you'll see it struggles quite a bit before it comes to its sad end. Because we didn't do anything with the low-level food placement planning or the trajectory planning at the lower level. That's all Boston done. So what we did was at the higher level, we did our local path planning, global path planning, and the traversability estimation. And we managed to pipe the low-level sensors of the robots into our LiDAR-based map so that we could do seamless planning from near field to far field. So at this point, it's still trying to perform its frontier-based exploration, trying to peek behind bits of rocks that it hadn't seen.
So is that like a hole that it's in? Or?
Yes, so there's a bit of a lip there.
Right, yeah.
And now this is Bluey.
So what, I mean, it's kind of just say what was actually damaged?
It wasn't damaged per se. It had the capability of standing up once it falls, but we intentionally disable that behavior because in some cases it would end up knocking the LiDAR around, and we didn't want to risk corrupting the map by having that self-right behavior. Now this is Bluey, so it's actually going through a puddle of water filled with pebbles. I think that was put in there to try and mess up LiDAR-based perception. Luckily, our SAM system didn't seem to mind. And that's an artifact. That's the helmet. That's the type of stuff that we're supposed to detect. And something pretty cool happens. If you observe, you'll see a bright light towards the left here. That's Bluey seeing fallen bingo for the first time. So that's the light of bingo. So that's that raised lip that it had fallen. And now this is Bluey valiantly trying to come back with all the data that it collected from bingo. And you'll see how difficult this terrain is. Notice the flow. It's not flat. It's sloped and slippery as well. And that's another rope. That's another artifact that we detected. And this is not someone joysticking the robot. This is fully autonomous traversal. Yep, that's end of Bluey as well. Mind you, this is all man-made. Just to give you an idea how good it was, DARPA spent over the 3 years, spent $82 million US running the challenge. So they didn't spare any expenses doing this. So at the end of it, that was the leaderboard. Because we tied for the top score, they had to invoke the tiebreaker rules. None of us knew the tiebreaker rules. It was in the rule book, but we have never looked at it because in the previous circuit events, nobody, like there were no ties, so nobody really cared about that. So we found out that the tiebreaker rule meant they were going to look at the timestamp of the last point scored. So whichever team scored the point the earliest would win. In this case, we were 46 seconds behind the other team. So unfortunately, we ended up in second. So I'll decipher some of the team names. I'm sure most of you are wondering who the teams are. So Cerberus, led by University of Nevada, Reno, but they also had Oxford Robotics Institute and ETH Zurich, plus two other companies, Flyability and Sierra Nevada Corporation. So a big consortium of universities and companies. Then that's us, number two. Number three was University of Colorado Boulder and University of Colorado Denver. Number 4, Explorer, was Carnegie Mellon University and Oregon State. I think you have one of your alumni who were there, Graham Best. He was part of Team Explorer. Now I think he's at UTS. And then CoStar, NASA JPL, Caltech, MIT. And then we had a couple of Czech Republic teams, CTU, CRAS, that is Czech Technical University. Coordinated Robotics was an independent team, and then Robotica again was a Czech Republic team. So as you can see from the list, we were in amongst formidable competition. And overall, we were quite happy with where we ended up. So in the end, our exploration wasn't too far off. Extrapolating from being 5th, 4th, and the missing data points in the claim circuit. Yeah, so it was a little bit disappointing that we could make the top, but given the circumstances, we're quite happy with where we ended up. You saw a lot about what the legged robots are doing, so I want to play a few videos of what the track robots are doing. This is from DARPA's YouTube stream. So they had a delayed stream showing what the robots are doing. Early in the piece, score 0, one of the robots going in. Score 17, that's where Bear was trying to go through, Brad was blocking the path, and that's another dynamic obstacle. That's something that I forgot to mention. DARPA also had dynamic obstacles. So when a robot goes through a particular path, they had these, what do you call them? It's not exactly trapdoors, but they had these things that would kind of fall behind and block the path. And they also had a wire mesh that would almost act as a Faraday cage to block communication going through as well. And they also had smoke machines. So when the robots entered certain parts of the course, they would trigger the smoke machines and fill the whole segment with smoke. So yeah, they were nice to the robots. And this is where score 21, 7 minutes to spare. That's when Bear launches the drone to get the smallest form factor to fit through the narrow gap. And at this point, this was Waypoint Navigation with the human supervisor, just less than 5 minutes to spare, with the drone off the back, trying to get the robot as close as possible to the other robots. While it's being driven, you see it's throwing out a comms node as well as it goes. The commentators that DARPA had there, they had some sports commentators commentating. There's another piece falling off the robot as it flies past. It was quite good. This is a view from our local navigation and global navigation system. So the voxels represent traversability estimations. The colors represent the traversability. So the purple voxels that you saw, they are virtual surfaces. So as the robot approaches the ledge, as it sees more of the information, that it updates the virtual surfaces, kind of coming back to the actual shape of the ledge. And the pink voxels are the fatal obstacles, voxels, and the green area is the traversable part. And here we are turning on our topometric cost, or the cost to go map. So this is coming from the global navigation graph that we have, and that shows the color. The color represents the cost to go from the current location to any one of the nodes of the graph. This is while doing a fully autonomous exploration mission. And here the robot turns around so that it can go backwards down the stairs, as I mentioned earlier. So you see that it detects the edge of the steps as fatal, so that it doesn't plan across that. And what DARPA did, even though we really wish that they did, but they didn't consider the mapping accuracy as a tie-breaking metric, but they did show the mapping performance and compare it across the teams. Anything orange is deviation from the ground truth. As you can see, we had the only map that didn't have any orange. According to DARPA's own metric, in the broadcast, they said 0% deviation, but in fact, they were rounded to the nearest integer. So our deviation was less than 1% from DARPA's own ground truth. And just to put things in context, the team that beat us, they had a nominal deviation of about 15%. And what this enabled us was also to win a superlative award for the most accurate artifact report. And here the error was 4.8 centimeters. And to put things in context, we would have still scored that point if the error was 500 centimeters, because the allowed tolerance was 5 meters. So we were two orders of magnitude better than the requirement in this case. And this is a post-process view of the collaborative map that our robots, the ground robots, did of the course. So these are the 4 ground robots. At least here, Bluey is blue. Bluey, Bingo, Rat, and Bear collaboratively mapping this area. And the ground truth is in gray, so you can only see the ground truth in this bit where we didn't send in robots. The rest of the area, you can't see the ground truth because our maps are pretty much overlaid with the ground truth. So that gives you an idea of the mapping accuracy that we got. And this is a 3D fly through of the same map. And what was interesting was a few days after the competition, I got a call from a company called Leidos. That's a fairly large defense contractor in the US. They're the ones who've been contracted by DARPA to do the ground truth survey of the course. So they told me that they spent more than 100 man hours surveying the course to get the ground truth. So they were asking, how in the world did you guys do it in less than an hour with a bunch of robots? Which was a good call to get. And something that we also did was we colorized the point cloud in real time on the robots. But due to communication bandwidth constraints, we didn't send it back to the base station. So this is not photogrammetry. This is a LiDAR point cloud colorized with the RGB cameras that we have on the robots themselves. And each of the robots are doing it in real time. And that information was available in real time, but because of bandwidth constraints, we decided not to send it back to the base station. Because in that way, we could actually very clearly see the artifact locations as well.
Yes, is the artifact identification just like visual, or is there a particular criteria or multiple criteria?
Mostly it was visual, but there were some artifacts like carbon dioxide concentrations and mobile phone detection using Wi-Fi and Bluetooth. So we had to have those additional modalities, but majority of them were detected using RGB.
Right.
We didn't use, that's a row. So we didn't use the point cloud to detect the artifacts per se, but we used the SLAM-based localization to do tracking of the object to improve the accuracy of the object detection. Because as you know, like each robot would have multiple viewpoints of the same object and multiple robots might see the same object. And the architecture that we had was once an object is detected, the report will be sent back to the base station and the human supervisor has a chance to verify that before sending it to the DARPA scoring server. Then we immediately know whether you scored a point or not. And we didn't want to bombard the human supervisor with tens and thousands of detections. So having that object tracking really helped us prune down the number of candidate object reports that were coming through.
The CO2 identification is an interesting one. I guess you have to integrate it with some kind of sensor.
Yes, so we used a CO2 sensor, but that too we used tracking because we had to keep track of the concentration going up.
Yeah.
And so we made the decision where you get the peak of the gradient, that's where you would report.
Right.
So the rules meant that they would have carbon dioxide released in a enclosed area, and as the location we had to report the center point of the entrance of that area. So if it's a room,
Right.
so we had to report back the location of the door if you detect CO2 in a room. Yeah, that was a tough one. So yeah, how did we do this? So the paradigm that we used was homogeneous sensing and autonomy on heterogeneous platforms. So that was the concept that we used. So this shows the many different platforms that we used over the years, not just the ones that we deployed in the finals. As you can see, we went through a variety of platforms. And what that meant was we could not afford the luxury of having customized software stacks per robot, because we had to very rapidly bring in new platforms over the course of 3 years. So it wasn't by design, it was almost by necessity that we developed this paradigm of having a common control architecture across the different robot platforms. So we had some basic assumptions that the platform would be able to make use of a velocity twist message coming through. And in some cases, like the track robot, we went all the way down to the low-level motor control, whereas with the Boston Dynamics robot, we interface at a fairly high-level API. And then you'll see each of our ground robots have exactly the same sensing payload when it comes to object detection and SLAM. That really helped us. And in terms of autonomy, all the ground robots had exactly the same autonomy payload as well. In this case, it's incorporated into the robot, but in these robots, you'll see what we call the barn on the back of the robots. And it was the same SLAM system running on all the robots, including the drones in a different form factor, because Emerson licenses Wildcat SLAM from us, so that's what powers the HoverMap product. And that allowed map sharing between the robots. So what I might have forgotten to mention was once the robots are deployed, even if they lose communication back to the base station, they still communicate amongst each other if they're within communication range. And the way it is set up is the base station runs exactly the same software that runs on the robots. So the base station is yet another agent in the setup. So each of the robots will be exchanging their submaps and navigation information amongst each other. And each of the agents would be, for example, solving the SLAM problem. And we know that there won't be a global unique solution because each of the agents would have subsets of information. But given the robustness and reliability of our SLAM system, we were quite comfortable that there would be consistency amongst the maps within tolerances for it to be okay. And the other very important thing is what I've mentioned here in blue. We had very, very rigorous testing throughout the 3 years, and we failed fast. For example, this was very close to my heart because Lego Robots is my research area. We built our own hexapod robot, designed it from scratch and built it. We deployed it in the tunnel circuit as well, but then we decided to fail it because we knew that it was not going to come close to the maturity of some of the commercially available platforms. While that was a great research platform, we knew that was not going to win us the competition. So we decided to deprioritize that. There's no point trying to compete with a company that had been doing Lego robots since 1998. So there were decisions made like that. And in terms of modularity, that's what I mentioned earlier, having that modular payload, having the autonomy barn and the cat pack across all different robots. So that modularity really helped us. And then also this common control architecture. And in terms of testing, every Friday for 3 years, we did integration testing and ran testing like as if it was a DARPA challenge. So we had one team setting up the course with the artifacts distributed. Then the operators were sequestered. They didn't know where the artifacts were on that particular Friday. time it, run it, then have a debrief at the end to figure out what broke. By next week, Wednesday, that has to be fixed. We test again on Friday. And we kept doing that for 3 years, every week. And that really helped us really bring up the maturity of the platforms. Because as you know, as field roboticists, we often have situations where we deploy the robots, there's one little niggly thing that you have to go and wiggle a USB cable, restart the computer, reboot your machine. None of that was possible in this challenge. Once the robots go in, no humans are allowed. So we could not afford that luxury. So we were forced to really push the envelope in what's possible in terms of robot reliability. And even the concept of having just shipped our robots and get somebody else to operate our robots. If someone asked me 3.5 years ago, I'd say that that's joking, because that wasn't even considered at that time. But the fact that we were able to do that last year, that makes us quite proud that we did manage to really push what was possible in terms of reliability of robots. And the other cool thing is we already commercialized a number of the components of this technology, like HoverMap. They've been selling products since 2019. So anyone around the world can purchase one of those. So they already have about 400 customers around the world. That's a pretty good success story. They spun out as 7 people in 2019, and now they're more than 150. So it's a pretty rapidly growing startup. And more recently, we commercialized this cat pack through a company called Automap, again, a Brisbane-based company. So you can buy exactly the same payload that ran on each of our robots from Automap. And for those who are interested, we have a couple of papers that describe the technology in a little bit more detail. And in terms of testing, we are lucky to have a really great site up in Brisbane, which has a fair bit of industrial setting there. We also built 300 meters of shade cloth tunnel just for the purpose of testing our robots for sub-T. And these are the environments where we did our testing. And this is fully autonomous, going through a narrow gap. And this is something that I'm very fond of. Having a robot going through a narrow gap, 2 centimeters tolerance on each side. That was pretty special. And we were very nice to our legged robots either when it comes to testing. But as you saw, all this testing really didn't help in the end. So why does this all matter? Why does it matter? So for us, it's not a CSIRO robotics group win or even CSIRO. I think this really is considered an Australian win, because we got a chance to showcase Australian field robotics capability at a global stage and shine a spotlight on it. And we also have matured and commercialized some of this technology. And the next cab of the rank is the multi-robot navigation stack, which I'm actively working on currently to set up an early adopter program, because we've got a fair bit of industry interest in getting their hands on it. And the other really interesting one is the third point, where this is an aspiration goal for us as well, to have this concept of not just one robot, but having a whole team of robots as a tool that can be deployed to solve problems in many different domains, where all you need to know is how to use the tool, not to build the tool. I think there's a big difference there. So where we could have a future where you have non-roboticist deploying not just one robot, but a whole team of robots to solve problems. And then we are also pretty keen on using this technology as a baseline and then build upon it. And that's where we are currently actively working on sending these robots into natural environments. And natural environments come with their own challenges. because in the sub-T domain, most of the environment was static, and we didn't have mixed environments. We didn't have to deal with humans in the course. Yes, there were dynamic obstacles, but they were not constantly moving. But in the natural environment, everything moves, nothing's rigid, nothing's flat. So that makes it very challenging. And the other thing that we've done is we've moved into field mobile manipulation. So we put arms on the back of our robots, and we're trying to do things like moving branches out of the way to navigate, trying to push obstacles out of the way and things like that, which is quite exciting. And the other thing that we did was, because the team that beat us had those robots. So we want to know what's so special about it. So we bought one. And currently we're playing with it. So that's Animal from Anybotics. That's a robotics company that's spun out of ETH Zurich. I do have a grudge against them because they just hired our top electronics engineer early this year as well. But we decided to do a bit of a test in racing these robots. So that's a Ghost Robotics quadruped as well.
3, 2, 1, go!
So this was an out-of-the-box config, full sticks forward, nothing special. So we realized that the Ghost robot has an interesting momentum-based controller. So even if you let go of the stick, it actually keeps going. Yeah, so thank you very much for listening. So that's hopefully that was useful.
Well, thanks, Navinda. That was a fantastic and inspiring presentation. So I'm sure we'll have some questions. Maybe while everybody's thinking of the questions, I'll kick one off. So you were working with a few different types of mobility platforms here. You've got tracked robots, legged robots. There was drones on the back of the tracked robots, although I didn't see as much that the drones were being used. It seemed to be mostly the ground robots getting about. What did you learn about different types of mobility in this sort of environment?
Yes, so unfortunately, the finals course was not a very drone-friendly course.
Right.
So in our case, the tracked and the wheeled robots, the tracked and the legged robots were quite capable of covering the environment without having drones involved. But in some of the previous circuit events, like the one that I mentioned, the urban circuit where we had to deploy robots in a nuclear power plant that had areas with very high ceilings, high alcoves, where they would have artifacts where the ground robots did not have visibility. So in that sort of an environment, the drones played a big part in being able to reach those environments. And they also had areas that could only be reached through a hole in the ground. So we had our drone flying off the back of our robot, actually finding a hole in the ground, going down a vertical shaft to get access to another level. So those things can't be done with a tracked or legged robot. But in the finals, they didn't have that sort of an environment.
And how about kind of tracked versus legged? Were there certain areas that one would work, the other wouldn't, vice versa?
Yes. So the tracked robot was an interesting find. Initially, we had smaller tracked robots that had terrible ground clearance. They would get stuck on the smallest bits of rocks and the tracks would come off. But then we discovered the BIA5 ATR. That's a beast. That thing can go over literally anything. And it can go over 60-degree inclines. And that robot is about 150 kilos. And it has a top speed of, I think, around 3 meters per second. So we had to scale down the speed. We were more interested in getting control authority at lower speed. So we capped it to about 1.5 meters per second. But the problem with that is it's wide. So it won't fit through very narrow passages. It can go upstairs, not very elegantly, but it can. So that's the reason for us to pick the Boston Dynamics pod, because it had a much narrower form factor and it could go up and down stairs more elegantly than the track robot. So that's where the distinction was. And because of the payload carrying capacity and the real estate that you have on the robot, only the large track robot could carry the additional comms nodes. So that was a limitation. So there were certain areas where we lost comms, but we had no way of sending the bigger robot that had the nodes to drop it because the passage was too narrow. So there were trade-offs there as well.
Great. Questions from you? Well, one comment and one question, I guess. So one is, you said one of the things you were most proud of is that you kind of offload the whole thing to a team of non-experts. It's really, I guess, inspiring to see that. And I know we have a spin-off here, Marathon Targets, those target drones. The CEO of that company said one of his proudest things is that they can give robots to essentially high school dropouts. They could do slam maps and all kinds of stuff without knowing anything about the animal. So I think that's really interesting that's something that's resonated too. In terms of that sort of next step in the manipulation, it's like if the task had been to collect the objects and bring them back, what are the big challenges that still exist?
Oh, I think the whole manipulation and grasping, that in itself poses a lot of challenges. Because when we started mobile manipulation, that's when we realized that there's a reason why manipulation and grasping are separately matured and studied in different labs. So that itself, I think, is a big challenge. But then the other challenge, again, something that we're going through right now, is mobility and manipulation sometimes doesn't go together, because there are some big challenges in being able to do manipulation while things are moving from a hardware point of view as well as a planning point of view. So I think that would be a challenge. And then in our case, we had a different ConOps because we knew we didn't have to bring the robots out. But if we knew we had to collect samples and bring them back, I guess we would have had a different strategy around it, and maybe be a little more risk averse, I suppose, because if you couldn't bring the sample back or the artifact back, then you would score a point. But yes, so that would be a slightly different challenge. And I guess probably more challenging than what we had as well. Could be the next one.
Yes. Yeah, sense if they are going to do the next one, or is it sort of on to the next thing?
The way DARPA have been running challenges, they don't seem to have like a next version of the same thing. The exception, I think, was the DARPA Urban Challenge, where I think nobody succeeded initially, and they had to have another one. But the other challenges, they seem to kind of move on to another thing.
Thanks. Any more questions? Any on that? No. Ali?
First of all, thank you very much. That is definitely exciting things, and I can understand the systems engineering challenges integrating all this stuff. Looking at the competitors, as far as I understand, they are using off-the-shelf components. So I think the intentional expected contribution are not the platform, but high-level integration of those sensors, I guess, or robots and sensors. So one of the interesting things I've seen, you are dropping communication units. Do they supposed to be active as well? So do they track actually the platform, or just relay? Or another question about the communication things is that off-the-shelf Wi-Fi stuff, or do you consider any other technology that you may actually extend the communication range on the ground?
Well, thanks for the question about the comms nodes. We had an active discussion about active nodes. We call them smart nodes, where can do exactly what you mentioned, but in the end we decided not to do that.
So there was no restriction in the computation?
No, there weren't any restrictions. So in the end they were relaying only, so they weren't doing any active tracking. The nodes that we used were from a company called Reagent. Not the mechanism that drops and opens up, but what's inside is the OEM version of it. So that's a company that's spun out, I believe, from UPenn. So they're based in the US. They build these Reagent nodes mainly for mining applications, and then they have a dual band 2.4 and 5 gigahertz band. And internally, they have some magic that happens where they can do frequency hopping and frequency band switching, and they perform really well in underground environments. So we built our communication framework on top of that physical layer, and then we designed a layer what we call mules for data muling. That is kind of a state-aware or content-aware protocol. So when the robots are within comms range, they actually negotiate to figure out what each of the robots have to avoid duplication of content. And then we also have a notion of prioritizing the type of data. So because we have map frames to share, we have navigation information, and most importantly, the object detections coming through. Unfortunately, in that particular scenario, we didn't have a way for the human supervisor to dynamically change the priority, but that's something that we're looking at. So hopefully I answered your question there.
I think everyone feels a great sense of pride when you say Australia's CSIRO came, tied first. I still think it's tied first. When you showed a picture of one of the either blue or bingo trying to figure out which way to go, there was a bunch of little circles representing the cost of each path. What type of cost do you measure, and is there any trade-off with the likelihood of success? The value of like the cost. Is there a guess at what the value of any path is?
So at that point, we are doing a task-based exploration. So in that paradigm, we send the robots on exploration beyond comms, and it's either chasing frontiers. So each frontier becomes a task, which has a cost associated to it. And the cost comes from, in that case, our traversability cost map. So there's a traversability cost coming from our LiDAR-based SLAM map. And then we voxelize it to get the voxelized representation that you saw. So it's a probabilistic voxel grid-based traversability estimation. So we have the conditions or the parameters of the terrain coming into that. And that's where we color the voxels. And what you saw is kind of a thresholded version of that. So at the lower level, the robot has more finer grained information. And that's what influences the cost there. But then there are some additional parameters that are based on the platform itself. So each platform would have its capability in terms of gradient, how steep can it go, and that also depends on the angle. So our path planning takes that into account, because a particular gradient, a robot might be able to go straight up but not sideways. So all of that is taken into account. So in the back end, this is a simplified version of it, but when there's a waypoint to go, the robot footprint would be kind of superimposed on it in various different orientation to figure out the cost of traversability, and that's what influences the cost to go. And then there are other tasks, such as dropping a comms node, for example. That could be another task that the robot is trying to do. So in that case, what you saw there, that was a pure exploration task. So trying to find frontiers that it hadn't seen. So frontier is the boundary between seen and unseen space. So each of those points or the tasks that robot had to complete going to a frontier in that case.
So the follow up on that, you mentioned the traversability estimation given the terrain sensing. Is there any kind of learning in that? So if, for example, if a legged robot or the tracked robot tries to traverse a particular patch of terrain and fails, does it then do any updating of the traversability estimation or the features or anything out to improve that?
We did discuss that, but in the end we didn't. So all it does is, if it's seen that, then it would transfer that information to the shared map, and then another robot will have to make their own decision given more updated information, whether it's something that you should do or not.
So going from a LiDAR to a traversability metric, is that kind of hand-designed features that are used for that?
So we have our point cloud coming in, and then we have the voxelized version of that, so that we are using something called the OHM grid. So we've open sourced that as well. And from OM, there are a whole bunch of heuristics that are hand tuned as to the timeouts and things like that, because it's doing ray casting. So which ended up with some very interesting scenarios as well, because we had certain heuristics as to when a voxel will get cleared. In the underground domain, we could assume that pretty much all the rays would have a return. But the same thing, if you use it in an open space, then we need to change the heuristics, because if it's in an open space, most of the rays would just go off and never come back. And depending on the tuning, we had a situation early on in the tunnel circuit where one of our small track robots was in front of a vertical pole. It was calculating something else, and after a while, that pole had disappeared because it was not moving at all. So in our voxel grid, that got eroded away, and then it went head on to it, and it kept banging onto it, because as far as it was concerned, that pole did not exist there.
Hey, we had a bit of a kind of culture wars in ACE class, etc. started off where on kind of making your own software and having a lot of other software in-house first having the time on the black box. Can you explain, like, discuss with us what the pros and cons were with having the track robot where you have total control and how to work with that?
So it wasn't a kind of preconceived philosophy that we had. We kind of had to do what worked, and we also wanted to not reinvent the wheel. If something was solved, we didn't want to resolve it. In the case of the track robot, what happened was the company that builds them, at least until now, they didn't build it as an autonomy capable platform. They built it as a police robot. The original version was 300 kilos with a pneumatic jaws of life type arm on it. So that was meant to be remotely controlled by first responders and police personnel. And it worked fantastically well when you have a joystick sticks forward, crashes through drywalls and things like that. But when we got the same control and tried to use it with our autonomy stack, it had absolutely horrible low speed performance because the controller was not tuned for it to kind of crawl. So that's where we said, now the existing controller doesn't work, so we have to scratch that and do it from the beginning. But we also had to do some upgrades. We had to change the battery chemistry on that robot because it had lead acid batteries. We changed it to LiFe batteries. Then we changed the motors because we wanted higher torque density for it to have that control authority at low speed. So we had to do all of that to get the performance we wanted. So that's the reason why we kind of went in and did that. And right now we're actually negotiating with that company saying, we want to buy an autonomy capable platform from you rather than us doing the work. So we've done a bunch of technology transfer to that company, and our aspiration is that we'll be able to just buy a robot from them and we can just interface it through ROS and it will all be good. Whereas the Boston Dynamics platform had all of that solved. Like at the lower level, we were very impressed by what it could do at the lower level. And it gave us a few different options where to interface. So you could interface at a waypoint level, or you can pass on a trajectory. But something that we did do, which we found out later on, none of the other teams had done. So that's the other thing. There were 5 teams using Boston Dynamics spot robots in the finals, plus 1 team using the animal robot. So there were 6 teams using quadrupeds. And we were quite surprised as to why we did so well with the spots, whereas the other 5 teams did horribly badly. Because we knew the platform itself was a really good platform, but we saw in the footage that they were tripping and falling like crazy. What we found out was most of the other teams turned off the low-level perception of the robot that helps it do footstep planning. The reason is they couldn't figure out how to integrate that with their high-level system, because they had to choose one over the other, and they decided to stack a lot of sensors, LiDARs and cameras on top of the robot, and then they essentially ran the robot blind, which, as you can imagine, leads to bad consequences. So what we did was we put some effort into integrating these 5 time-of-flight sensors that the robot has, which can see almost under the robot itself. Then we piped that into our LiDAR-based map. So in our own map, we had the sensor information from the low level as well as the high level. And that allowed us to do seamless path planning. And I believe that's one of those things that got us over the line, especially with these robots, which in hindsight, it's mind-boggling as to why the other teams didn't do it. I think it comes down to amount of time, availability to kind of do all of those things. But hopefully, it was a long answer to your short question. But hopefully, I answered your question.
Any other questions?
Bonus question. What made you move away from exopods? Because I know your initial entry was at that kind of slide.
Yeah.
Look,
it's a pure timing and capacity bandwidth thing, because we had about 2.5 FTE dedicated for about 2 years building that tech support. But compare that to close to $100 million per year budget that Boston Dynamics had since 1998 building this. So it was a no-brainer in the end, because purely from a performance at the competition and reliability point of view, we knew that we were not going to get there. If we had another maybe 5 years to mature that platform, yes, it could have been competitive against that sort of robot. But in the end, we had to make the call because we knew that it was not going to win us points compared to the other commercially available platforms. Because at the beginning, 3 years ago, this wasn't commercially available. We couldn't buy it. But last year, we could. So we actually bought this in April last year, and we competed in September. We managed to fully integrate our software stack and test in less than 2 months, which is huge. Whereas the previous one that we used was the Ghost Robotics quadruped, and the timeline was around 6 months where we got to that point with that robot.
So if there are no further questions, then let's thank Navinda once again for
Before I finish, one last thing I forgot. The project cost for the 3 years for what we did was $10 million US. Out of that, 4.5 million came from the US government, from DARPA, and 5.5 million came from CSIRO co-funding. At the end of it, we won $1 million US as prize money. And it was recently announced, so it's public. So we ended up using that money to set up a scholarship, PhD scholarship fund with QUT, targeting females and candidates from underrepresented communities to study robotics. So that's what we did with the prize money. Just wanted to let everyone know.